you probably have been thrown a lot of 3-letter, 4-letter acronyms and don't necessarily know how these things tie together. But I think it's also good that I'm doing it now as kind of the last step, so that even if you wonder like some of the things that you heard, you may not be fully aware of the implications. I am now going to be having the opportunity to hopefully stitching everything together for you. So for those of you, I don't know who don't know me, but for those of you who don't, I have been focused on the UEFI ACPI stuff for a long time. This dates back to the Itanium days with Intel and later on x86 ARM. I actually did something for RISC-V as well, very dangerous. And I also helped Long Arc to get into the ACPI UEFI also. Now my task is a bit more broader, not just the firmware side. So as you can see, I kind of put my footprints everywhere. But anyways, what I want to talk today is about the overall system firmware architecture, so that the acronyms you heard, how they fit into our overall scheme, and also more importantly, how UEFI and ACPI fit into this scheme, right? And so show you a few examples. So this is kind of the diagram that could potentially help you understand how we stitch everything together and where these firmware technology fits into this. And you probably have heard about the term SBBR, BBR, BBSR, and system ready, right? All these things. So this is a good diagram to show where these things are fitting and what they are. Why do we have all these acronyms? What are these technologies that we try to put together to do in this system architecture? So we have a few different flavors. I think before last November, we actually had many different flavors, like 4 different flavors of system ready, because we were just trying to figure out, like in the market, there are all kinds of solutions, right? We have the more traditional PC way of using UEFI ACPI. We have more of the embedded space where U-boot and device tree were dominant, and then we also have people. I think you heard on Tuesday, David, who was very interested in Linux boot, and so we used to have like 4 different bands or recipes or profiles to support different purposes, and it's very confusing. So last November, we actually, in the System Ready program, we reduced into like major 2 bands. So basically, this is one of them, right? This is what we call the System Ready band today. What it does is that actually, define the hardware and firmware requirements so that the general purpose operating systems like Windows and Linux distros can work on these systems, whether it's PCs or DPUs or IoT devices or servers. It doesn't really matter. As long as they use the similar approach, to get the system up and running, then this is the system ready band. And so typically today, this is the most mature thing that we have today is for server space. And so in this diagram, you can see that we have this base system architecture to define the baseline hardware requirements for the ARM platforms. This is needed for this band, this system ready band, because the operating system not only depend on the APIs into the firmware, but also it assumes the hardware interfaces, the register interfaces, for example, PCIe ECAM to find PCIe devices, right? And also, of course, the what kind of features are available on the ARM CPUs and all that. So the base system architecture gives you the view of the hardware requirements. And it has two flavors as well. It has the physical, if you're building a real SoC, you need to have this kind of requirements for the physical bare metal devices. But this also could apply, some parts of this could also apply for the virtual environment. Indeed, if you're talking about the cloud service providers, what you have as a customer from the cloud service providers are not the physical bare metal hardware, right? They gave you the cloud instances through hypervisors. So, but in that kind of environment, you basically have the hypervisor kind of pretending, the hardware pieces are there to the operating system. So that's why I said there are two aspects of this. And then the server-based system architecture, which is called the SBSA, is a supplement on top of it, where it would cover some of the server market hardware features that the operating systems can depend upon. I think if you look at some of the ARM architecture specification, like the CPU architecture, you could have features that are, very flexible for people to implement, because that document is supposed to cover all of the ARM devices, right? So when they talk about a feature, that could have, hundreds of ways of implementing, but the standard operating systems may not be able to handle all that, because then you have to customize for all the devices. So the SBSA is really there for giving you the ability to say, for servers, for this particular feature, this is how the hardware should be implemented, so that the the operating system can have one way of dealing with it. Then on top of it is what we call the BBR, the base boot requirements. These are the firmware requirements related to the UEFI ACPI interfaces, related to other standard firmware interfaces. So there's one recipe in there. So today in that document we have basically three recipes. One is called the SBBR. Forget about what this SBBR means, because it initially was for the server market. So it was the server BBR basically. But what we found out is that there's not really a lot of differences between the requirements for servers versus the requirements for PCs and DPUs and Windows IoT devices, right? So basically the core of that SBBR is UEFI, ACPI, SMBIOS, plus a few ARM-specific interfaces. I have another diagram later on to show you that. So we didn't want to spell out what SBBR really means. It's really just for if you think about it, anything that requires ACPI that the OSs are expecting, that is SBBR. Then on top of that, you see the base boot security requirements, so the BBSR. Well, historically, we initially didn't care about security. I think that's the common scheme, right? So people kind of try to get the system up first and then think about security. But these are like the secure UEFI secure boot, TPM measured boot, firmware secure update, and all that kind of features. So that's defined there. But we are looking into combining that with the BBR in the future, because what happens there is that it's basically a bunch of firmware requirements plus the TPM, but we can put TPM into the hardware side of the requirements as well. And so what that does is that it forms the interfaces, hardware and firmware interfaces, for the standard distros of OSs, commercial OSs like Windows or the Linux distros. As to how you build the hardware, we also have an architecture called chiplet system architecture. So Nowadays, chiplet is very popular, so we have a way to defining how you, to partition the different subsystems. And on the left-hand side for servers, I kind of mark it in a different color. For servers, we also have this SBMR, which is the system-based manageability architecture requirements, right? So this is out of the desire, like initially when we were doing the ARM-based servers, every SoC had their own, BMC solutions, right? Sometimes I think if you look back to some of our test chips, the N1 SDP, that was not even a standard BMC. So everybody have different kinds of management commands, management interfaces. That's not good, because when you try to deploy into your customer's data center environment, you can't really assume that this customer is going to buy everything from one vendor, right? So that triggers us to figure out how we want to define the manageability interfaces there as well. So this is like IPMI, Redfish, MCTP, PLDM, all these things that we talked about in the past few days. So this is a little bit ahead of what we are going to be publishing next Monday. So today, so I'm kind of giving you a little bit of a hint into next week. So today, right, the system-ready band is only on the right-hand side for you to get the OS up and running. But by next Monday, this system-ready band is also going to include the SBMR as one of the required elements for the servers. So good with that picture, right? So changing gear a little bit. So for the embedded devices, this is mostly likely the traditional IoT embedded devices that only runs embedded Linux, right? And not necessarily running Windows, because Windows requires ACPI. So this is the embedded Linux devices, and also potentially automotive devices as well. So in this area, what we have is we don't have a requirement on hardware, if you notice, right? Of course, if you do an SoC based on the BSA, the hardware requirements, that's great, because you can now support either one of these approaches, depending on the market. But if you don't do the BSA, you can't support the previous system-ready band, but you can support this system-ready device tree band. The difference here is, as you notice, there's no requirement on the hardware front. Everything is described to the operating systems through EBBR and device tree. EBBR is basically a set of reduced UEFI requirements for the embedded devices. And the BBSR still apply. In that market, they also want to have secure firmware update. In fact, I think the session the other day about the European cybersecurity requirements, right? They want to have OTAs and everything needs to be secured. So the BBSR is also critical there as well. So as you notice, this EBBR approach is like adding the reduced set of UEFI interfaces to Linux, so that now you can use the bootloaders like Grub to separate the development of the operating systems from the embedded devices, right? So this is what we have been pushing for in terms of the embedded IoT market, laying the UEFI interfaces on top of the embedded devices. I have another picture to show you about that. You can still use U-boot. In fact, if you look at the U-boot code base now, the UEFI interfaces are supported, right? So you don't have to use EDK2, but of course you can. You can use EDK2 with device tree to form this, system-ready device tree effort as well. The chiplet side may not be too important in this market for the embedded space, but for automotive, maybe still. There is also, I'm also hinting a new thing called platform fault detection. This is an interface also designed for the automotive space, and it is not there published yet, but by Monday, you should be able to find this spec. All right, so I'm just talking about firmware here. I'm not going to spend too much time on the hardware requirements. So these specifications are public. We have this consortia, basically, anyone with NDA with ARM could participate in that consortia, and basically we work with everyone, right? This is not something we dreamed up by the folks only in ARM, right? We talk to OS vendors, talk to silicon vendors, BIOS vendors, everybody, right? So we form these specs. Using the QR code, you can find the specs. And as I said, the SR and BBR are eventually going to be merged together. I don't know the timeline yet, but that's our intention. And I think earlier today, Ed Heyer talked about the UEFI SCT, FWTS, and also the system-ready ACS, right? So the system-ready, we have the compliance test suite called ACS, Architecture Compliance Suite, that we can verify whether the target system is actually compliant to the specifications that we developed. It's not just the firmware compliance, it's also the hardware compliance for the system-ready band. We actually encourage the partners to include these test suites into their certification program. We have been working with NVIDIA quite a bit, and in fact, the version 1.7 that they just released the other day already have quite a bit of these ACS into their tool called NVSSVT. Server manageability, I talked about. It's a separate spec, so you can also use the QR code to find. I think it fits into this conference because during this week, I think mostly because of OSFC, it's kind of like both the system firmware side and the BMC side of the stories are being told, right? So we also have a very good specification now for covering the BMC side of the story also. And we developed the ACS for this as well. That's why we now can put the SBMR compliance into the system-ready testing. Well, so this is the diagram I was alluding to. So for servers, for PCs, for most of the DPUs, and also Windows IoT devices, as long as you require ACPI, this is what we call the SBBR recipe, right? So the SBBR recipe basically means that we want to support the standard OSs without modifications. And so in terms of the firmware interfaces, it's basically the full UEFI services, the boot services and runtime services and protocols that are referenced by the SBBR recipe, ACPI, SMBIOS. In addition to these industry standards interfaces, you notice that I think the previous sessions talked about the SMC calls and the PSCI flavor of it, and I think the previous mention of the platform fault detection is also one of these kind of flavors. So we do have this other interfaces that actually the standard OSs use on the ARM platforms to communicate with our system. And so typically, when we have these EDK2 type of code, okay, so let me just say, when we define the SBBR, we focus on the APIs and the interfaces, right? We don't really, in this effort, we don't really care, which code base you use. So, most of the people in the effort of developing this would be using EDK2, but Microsoft certainly uses Project Mu. And if you hear David Hu from Google talking on Tuesday, they're trying to use Linux boot, right? So Linux boot, we have spent time before to initially put Linux boot on top of a minimized EDK2 implementation to directly just launch Linux using the KZAC. But that's why in the BBR spec today, you can find that there is a third recipe called LBBR. But that's only for a very special environment, like certain cloud vendors wanting to do it that way. And so we kind of stayed a bit away from that after we actually developed the solution with the cloud vendors. In the first phase of LBBR, we did the Linux boot on top of a minimized, EDK2. And then they also find out that some other people, at least, didn't quite like EDK2 at all. So then there was an effort in phase 2 where we replaced the minimized EDK2 with core boot. When we tried to do that, I think they were doing it on x86 as well. It was very interesting that the development of the Linux boot solution on x86 machine assumed a very ancient BIOS interface, int15 EA20, right? And unfortunately, we tried to use UEFI to replace all that before, but the core boot effort for Linux boot went backwards and assumed that interface. That caused a problem for us because on ARM, we don't have these software interrupts, right? So we had to work with 9 elements, actually, and developed a UEFI shim, the only purpose of which is to kind of, replace the int15. Anyway, so far, right, we had that solution. Now, if you went back to the talk David had, they are now putting the UPL on top of Linux boot. Okay, so when you have the UPL, that means you potentially have the full UEFI interfaces, right? And when you do that, well, for the system-ready effort, we don't care, right? If you use that, UPL plus Linux boot plus core boot, fine, or EDK2, whatever, right? So, but now I have a problem that we're going to be investigating. We have the shim I just mentioned, right, which presents the memory map thing, and now you have the UPL. Okay, so who's actually reporting the memory map, right? So these are the kind of the caveats that we have to look into before we say, okay, abandon the LBBR and just do this SBBR. But hopefully, after we dig through the exercises, this is the ideal case, eventually, that I wouldn't care how you do the SBBR. You can do EDK2, you can do Mu, you can do Linux boot, or however, but as long as they present the interfaces on top, we're fine. Now, I think, Felix talked about the OpenSFI, right? And Alok was like, "Oh yeah, this is great. Can we do this?" So the purpose of the OpenSFI, as I understand, is really the cloud vendors and OEMs, as they try to put solutions across the CPU architecture, they would like to have the top portion of the host firmware to hopefully stay the same, because they have invested a lot into that space, right? So hopefully that the bottom side could be somehow standardized, that they can just put the host side of the system firmware on top of the silicon initialization. So think about SBBR as the kind of a northbound standardization after that we have done. The OpenSFI is more of a southbound silicon interface that the OCP side is starting. And it started on the server side, but I think Alok has been talking to me like, well, this might apply to the client side also. Yeah, so this is going to be interesting. I don't know when we will be able to do that. Anytime you're trying to put a new thing into this, right, it's going to be challenging. And also the CPU architecture are very different, right? You have SMM in x86. We don't have that in ARM, right? So, and we also developed the Trusted Firmware A is ARM's effort to kind of standardize that area. So hopefully everybody is following that, but ARM doesn't have really a way to dictate all the silicon vendors are following this, right? I don't know for sure that everyone is on this Trusted Firmware either, right? There may be some, we have a very vast ecosystem, so people can do whatever they like, but we at least try to put in this Trusted Firmware, which is also an open source effort hosted by Lenaro, right? So then how does OpenSFI fit into this whole story is something that we are going to need to figure out. So what I have been telling the OCP people is like, okay, even between Intel and AMD, that portion is not that similar today, right? So you guys work out the the problem first, and then I already have people on ARM, from ARM on this task to watch if any of the interface designs are kind of broken for ARM. So hopefully through that effort, maybe it needs a 1.0, 2.0 versions to get there, but we are actively participating. And then on the EBBR side, as I said earlier, our focus is on the interface side as well. So as you notice, the difference between EBBR and SBBR is really that the UEFI interfaces may be reduced. This is mostly for the embedded market, where some of the support is harder to fulfill. And then, of course, also the device tree rather than ACPI in this effort, right? This is like, traditionally a lot of these ARM IoT devices are based on, these embedded Linux or BSD using device trees. So it's very difficult for the ecosystem to change that behavior. Even adding, just asking people to add UEFI on top is not that simple. But through the system-ready device tree effort, we are trying our best. In terms of the code base, again, for EBBR, we don't care. You can use EDK2. A lot of people now use that. Well, not a lot of people. Some people are using that, just because inside of a company, you can kind of commonize the code base across all the products, right? But I think traditionally, a lot of people are still using U-boot. But, we have a lot of people putting efforts on making sure the UEFI services are supported on top of U-boot. And I think earlier Samuel talked about the ACPI specifications. There's another set that is really the ARM-specific firmware specifications. So I think Samuel touched on some of that, right? The SMC calls, PSCI, SDEI. We also developed with Microsoft and other silicon vendors on this DRTM architecture for ARM as well. We have mechanisms for secure firmware update. Some of the true random number generator interfaces as well. Management modes interface, right? The STMM that people talked about throughout the conference. ARM architecture supports that. I think, Samuel mentioned the FFA a few times also. So all these are published specifications. The links are there. The platform fault detection interface would be another one. I don't have the link, so that's why I didn't add it yet. It should come up next Monday. And this is the set of ACPI specs that Samuel already mentioned, so I'm not going to go through them. And these are all public specs as well. Some of you may heard that we also have been doing a PC side of the work. So we are just borrowing what we have done in the server space, right? So this diagram looks almost exactly the same as the server piece. The only difference is really that instead of the SBSA supplement for server hardware features, we are looking into this PCBSA supplement, which we actually published the version last November. But if you look at the left-hand side, in servers, we have the SBMR. On PCs, we don't yet have the remote out-of-band management thing yet. The reason is that on the server side, the flagpole is very clear, right? Because BMC, Redfish, IPMI, these are what the server, data center people expect. So we're just trying to kind of, catch up to that and then define some new things, for that. But for PCs, well, even Intel and AMD are very different. There's some standards, right? The Dash and maybe Redfish could be used. So this is something that we haven't spent our time yet, but certainly would be interested in looking into. And this may not have to be an ARM-specific thing. We'll have to see. Right, so I'm not going to talk too much into this one. I was hoping to show you as an example, but I think in one of the earlier sessions, Samuel actually had this diagram as well. So UEFI, ACPI, EDK2 is only part of the firmware, system firmware pieces, right? We have the BMC on the server side. We have a lot of the controller, the supervisory firmware for our microcontrollers attached to the SoCs. And this applies to servers. It applies to other devices as well, PCs also. Not going to talk too much. I think my time is already kind of over. And then we also, on the ARM designs, we also have this flow, as to which one loads which, right? So I don't think this is too important to this conversation, but, just for folks who are new to the ARM ecosystem, we do have a way to define different pieces. This is also just from ARM perspective. Not all the silicon vendors are following that necessarily. All right, any questions?
Okay, all right. Thank you, Don.